over an older homework assignment from Unit 1 having to do with binary and decimal number conversions. You can find it under the classwork section of our Google Classroom under Unit 1, and it will be this assignment labeled Flippy binary and decimal number conversions. So before doing this assignment, I covered what binary and decimal number systems are. So decimal number systems are basically the number system that we use from day to day. It's base 10. Okay, so this is decimal. So I don't mean like decimal like 0.105 or whatever. I just mean base 10 numbers here. So these are decimal numbers. And binary numbers are base 2. So base 2 is binary. So why are they called this? So base 10, the numbers that we use every day, we have these place values. So like we have our ones place, tens place, and our hundreds place. And if we keep going to the left, we'll have thousands, 10,000s, 100,000s, millions, etc. But this is enough to kind of get the idea. So if I had a number like 299, technically it's just these symbols, 299. But the reason why we know that it's 299 is because we have two 100s, so that's 2 times 100. We have 9 tens, and we have 9 ones. So if we calculate what each of these is, 2 times 100 is 200, 9 times 10 is 90, and 9 times 1 is 9. So when we add that all together, it's 299, the value. Base 2 is basically the same thing, but instead of having our place values multiply by 10 each time. So notice how for the ones, we can say that if we have base 10 to the 0, that's the same thing as 1, since anything risen to 0 is 1. If we say that this is 10 to the 1, that's our 10 spot. And then if we say this spot is 10 to the 2, that's our 100 spots. And then we can keep going with 10 to the 3 being our thousands, and so on. With base 2, we have 2 as our base instead. So we would have 2 to the 0, which is also our 1 spot. 2 to the 1, which is our 2 spot. And then we can keep on going to the 2, which is our 4 spot. And you see that same thing up here. This is what we are using to kind of learn how to count in binary. So in the classroom, usually I would have everyone make a paper version of this where we can flip things. Like you see zeros here, we could flip these to be 1 values, and I'll show you why that's so important. But since we're not in the classroom, you have this digital version linked here in Google Classroom that you can use. So this is what I'm going to be using to show you how to count in binary. So if I wanted to make a number in binary, it's very important to know that the only value I can have in any place is a 0 or a 1. So in base 10, we know that we could have more than just 0 or 1. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, up to 9 until we need another place value. For binary, it's only zeros and ones. So let's, I think it'll be easier for you to understand if I show you an example. So I'm going to open the activity guide, which was the homework for this assignment here. So if you open this up, I believe that you will only see these 3 filled out. And the idea for this first section is to create the decimal equivalents, so the decimal numbers, for every 4-digit or 4-bit number in binary. So if I have, so I'm going to just ignore these bits on the left because we are only dealing with 4 place values or 4 bits. By the way, bit is short for binary digit. Binary digit is bit. So we're dealing with these first 4 bits here, which means that the lowest value, of course, we can calculate is 0, and that's with the zeros in each of these positions. And that's because if we take this, if we say 8 times 0, well, that's 0. And if we say 4 times 0, 4 times 0, that's also 0. And then 2 times 0, that's also 0. And then we have 1 times 0, and that's also 0. So if we add all of that up, it is just 0, which is our base 10 number. Okay, so in 4-bit binary, 000 is decimal or base 10, 0. All right, so to count up, what I want to do is I want to flip this bit to 1. Okay, so as soon as I do that, I now see that, well, all of these are still 0. I'm not going to bother even putting those down. But now what's different is that I have 1 times 1. So that's going to be 1. So the important thing to see here is that the only digit that has any impact on the overall value in a binary number is a digit or a bit, binary digit, that is flipped to 1. Okay, so if you do not see a 1 in any other place value, that means that it's not going to impact the overall value, and you don't have to add the numbers that are above them. Okay. All right, so this next value here that I put 0001 calculates to decimal value 1. And then we want to count up. We want to represent decimal value 2. So in order to do that, we are then going to unflip this one and flip this one to 1. So now we see a 1 in the 2's place, and that's the only value that we're going to count. So this is going to be 2. There's no value to add here, no value to add here, no value to add here, since this is the only one that's flipped to on. So for this next one, 0010 is 2. And then you can kind of see a pattern going on here. So if I wanted to make 3, this is the first time where we see 2 different bits flip to 1. Now what happens is now we're adding together the 2 and the 1. So notice how it's not really super important that I say 2 times 1 and 1 times 1, because those are always going to be the same thing that they are. So to make this a little bit easier on yourself, all you have to see is that if there is a bit that's flipped to 1, that means you're going to add the place value. Okay, so in this case, there are 2 bits flipped to 1, so we're going to add these 2 values together, 2 plus 1, and that's going to be 3. So then we know that in 4 bits, looking at just these 4 place values, the binary number to represent the value 3 is 0011, which we put right here. And now, in order to get the binary number 4, we need to unflip these guys, and we're going to flip on the next bit. So we're going to flip the 4-bit, and that already is 4, so we don't need to flip any others. So the 4-bit binary number for 4 is going to be 0100. And then in order to get the next number, which is 5, we just need to flip the 1-bit. So now 4 plus 1, that's 5. So that means in binary it's going to be 0101, which is what we have here. And then to make 6, well, we could just unflip this guy and flip the 2, because now we see 4 plus 2 is going to be 6. So 0110 is going to be the binary number for 6. And then to make 7, we just need to add one more. So now we have 4 plus 2 is 6, and then plus 1 is 7. So now binary number 0, 1, 1, 1 is going to be 7. Now, how do we make 8? Well, we see that the next place value is an 8, so we're going to unflip these and then flip this position. So now we've got only 8 flipped. So now 1, 0, 0, 0 is going to be this next binary number. That's going to represent decimal or base 10, 8. Now, in order to make 9, we just need to flip the 1 bit so that we have 8 plus 1. So 8 plus 1 is 9, and now we have the binary number 1001. And then how do we get 10? Well, if we flip this one, that's going to be too much. So 8 plus 2 is what we want. So that's 1010. And then to make 11, we're going to go ahead and flip this ones place again. So now we have 8 plus 2, which is 10, plus 1 is 11. So now I know my binary number is going to be 1011. And then I need to make 12. So I know that 8 plus 4 is 12. So that means I need to unflip the 2 and the 1, and then flip the 4. 8 plus 4 is 12. So I know my binary number is 1100. And then I also need now 13, so I could add 1 to that, so I'll flip the 1's bit. And 8 plus 4 is 12, plus 1 is 13, so I know that this next binary number is going to be 1101. And I need 14 now, so I know 8 plus 4 is 12. I need 2 more, so I'm going to unflip the 1 and activate the 2 here. So 1110 is going to be my next number. And then finally, for 15, all of these are going to get flipped. 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. So it turns out that this is the highest value I can represent in just these 4 bits. Anything past that, I would need to add another bit. Okay, so 1111. For the next part, if you notice, what do you notice when you compare the odd numbers with the even numbers? So if you take a look at these, so here's an odd number, here's another odd number, and then kind of comparing them to the even numbers, you'll notice that all odd numbers have a 1 in the 1 spot. And that's because it's the only place value that's not even. So in order to have an odd number in binary, that last bit, the 1's bit, needs to be flipped to 1. So you can say all odd binary numbers have a 1 in the 1's place. This is because it is the only odd place value, right? All the other place values are even, and if you add even numbers together, you're going to get an even number. So you would need an odd number to make a value odd, or an even value odd. Okay, so this next one, what you want to do is you want to complete the chart with all the 8-bit binary numbers that have exactly 1, 1. So I believe when you start out on yours, you might only have these 2 filled out for you. So I want to kind of make it clear what they mean by 8-bit binary numbers that have exactly 1, 1. So let me put this back over here. So for this exercise, we're going to use the complete Flippy do. So this is 8 bits. Remember, bits are binary digits, so each of these place values is a binary digit or a bit. And you can see we have 1, 2, 3, 4, 5, 6, 7, 8 of them. Okay, so we're going to use this entire Flippy do for this one. So what they want you to do is they want you to find the decimal values of each 8-bit binary number that have exactly 1, 1 in it. So this number, for instance, has only 1, 1 in it. And what you'll do is just kind of add, or actually just look at the place value and that the 1 is under, and that's going to be the value. So the 8-bit number 00000001 is going to be equivalent to decimal value 1, so which is what we have here. Now for the next number, what we want to do is we still just only want to have one in this entire number. So we'll go ahead and unflip that one and just flip the next value. And so that is going to be equivalent to whatever the next place value is, which is 2. So our next value here, 0.00000010, is equivalent to decimal value 2. For the next one, we'll unflip that guy and flip the next place value. So now we have 4, which is 0.00000100. And then notice that the next place value is going to be 8. We'll flip that one. So 0.00001000 is going to be 8. And then I went ahead and kind of filled in the rest of the 8-bit numbers for you. So as you flip these, it's just going to take the next place value. So the next one will be 16. And then as we flip the next place value, that's going to be 32. And then as we go to the next place value, that's going to be 64. And then finally, if we activate the largest place value that we have in this 8-bit number, it's going to be 128. All right, so now moving on to convert these, we are given 2 tables. The one on the left, you're given binary numbers that you have to convert to decimal, and then on the one on the right, you are given decimal numbers that you then have to convert to binary. So let's get started on the one on the left first. So what we could do is we could just plug in the numbers into our Flippy-do and then add the place values that have a 1 under it. So if you see something that only has 3 place values, that means that you're going to use the 3 smallest place values on the right here. So we should only be using these 3. So this first number is 100. So that means that the 4 is activated here and nothing else is. So this number is going to be decimal number 4, represented by 4 bits of binary. The next number is 101. So we'll go ahead and activate this one right here. So now this is going to be 4 plus 1. So that's going to be 5. The next one actually uses 4 bits. So we want to use this next largest bit here as our 4th bit. And that number is 1101. So if we add these numbers together, 8 plus 4 is 12, plus 1 is going to be 13. And then now the rest of these in this table actually use the entire Flippy-do, so we're going to use the whole thing. And for this one, we've got 0, 0, and then we'll flip the 4th place value, which is going to be our 16th place. And then we will flip the rest. Okay, so if we go ahead and add these all together, it's going to wind up being 31. And I'll show you why. So this place value here is 32, which is going to be 1 more than all of these added up. So that's how I can quickly kind of calculate that. And if you don't believe me, you can go ahead and add up 16 plus 8 plus 4 plus 2 plus 1, and you will get 31. So this value right here is 31. And for this value right here, we've got 0, 0, 1, and then the rest 0, so we know that it's just going to be 32. And for the next value, you got 1, 0, 1, 0, 1, 0, 1, 0. Okay, so now we have 128 plus 32. And then we've got 8 plus 2 plus 1, which is 11. So we'll add all that together. And that's going to be 171. And then for this last one, we've actually got all ones. So we could use our shortcut, but our shortcut would be to take 1 less than the next place value, but we don't see a place value here, so we have to kind of know what that is. And we know that it's going to be 2 to the 8, but we also know that if we look at these are really just doubling in size. So like 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8. So we know that this next place value is going to be 128 times 2, which is 256. And if we know that if all these are 1s, it's going to be the sum of all these values up here are going to be exactly 1 less than this next place value. So this value is going to wind up being 255. And once again, you can test this by adding up these numbers individual, and you should arrive at 255. So that's 255. Another quick note is something that you will need to understand is you might be asked a question such as how many different values can you represent in 8 bits? The number of values you can represent in 8 bits is 255. So notice you can count up to 200, the number of different values that you can represent in 8 bits is 256. Now, don't get this confused with the highest value you can count to, which is 255. Because you have to actually count that we start at 0. So if you include the value 0, that means in 8 bits you have 256 different values that you can represent, 0 through 255. So just a quick note if you're planning on taking the AP test, that they might throw that in. All right, so now we'll do the opposite, decimal to binary. I think a good trick for doing this, if you're using the Flippy is I would look for the largest place value that is closest to the number that you're trying to calculate or convert, but don't exceed it, right? Because 8 might be close to 5, but already you've gone over, so don't flip that one. 4 is really close to 5, so we'll flip that. And I know that 4 is 1 less than 5, so I need to add a 1. So this is going to be binary 5. And it doesn't actually say like how many binary digits to represent this in. So important note here is that this is 5, this is 5, oops, this is 5, and so is this. Right? It just depends on how many binary digits you're actually using. So if it doesn't specify, I would just use the smallest amount. So just 101, and that's fine. But I certainly wouldn't dock you any points if you put those trailing zeros there in the front. All right, for 17, the closest value that isn't bigger than 17 is 16. And then I know that's just 1 away from 17, so now I have this value 10001. And then doing 63, I know that if I have all 1s in the smaller place values before a number, it's going to be 1 less than that number. And so I know that 63 is 1 less than 64. So I know that if I activate all of these, once again, you can test this, but all of these numbers are going to add up to 63. So that number is going to be 111, 111. And if you feel more comfortable grouping these in groups of 4, you can certainly do that. You can do it like this or like that. Whatever formatting is easiest for you, but I'm just going to go ahead and put the smallest number of digits that I can get away with. All right, 64 is quite easy because that's one of our place values, so we'll go ahead and 0 these out and turn on the 64-bit. So that's going to be 1 0 0 0 0 0 0. For 27, we're going to use that same trick. So we have 128, and 127 is 1 less than 128, so I'm just going to activate all of these smaller place values. So that's going to be 1 1 1 1 1 1 1. For 256, so this one's tricky because the biggest number I can represent with these 8 bits is 255. So for this one, you would have to realize that you need to add another bit here. So the 2 to the 8-bit, which is the same thing as this number doubled, 256. And then we could 0 these out. So these are all zeros, and then this is a 1. So that's going to be 1 and then 8 zeros. Okay. And then to make 513, so we've got 256 here. So I want to find out, actually let me zero these out real quick. I want to find out if I can count up that high in 9 bits, right? So this is my 9th bit. And to figure that out, I'm going to go ahead and calculate what the next highest bit is. Because if it is bigger than the number I want to calculate, then maybe I can still use just these 9 bits to calculate this. So let's see. So double of 256, 2 to the 9. So that is going to be 512. All right, so it looks like I need, this actually isn't even going to be enough. So 10 bits is too small, so it looks like I need, actually what I need is, I can't just represent this number with just this place value. I would need to add 1. So it turns out that I do need 10 bits to represent this number. So it's going to be 10000000001. Okay, so that's going to be 1 0 and then 7 more zeros and then a 1. So 1 1 0 1 2 3 4 1 2 3 and then a 1. And again, you could test that out again by doubling these numbers. So that's 256 and that's 512, right? So if I have a 1 there and a 1 here, that is 512 plus 1, which is 513. All right, so then the rest are just checking for understanding questions. So when you add a 0 to the right of a decimal number, it multiplies its value by 10. For example, 15 becomes 150, and now we need to think about what similar result happens to the value of a binary number when you add a 0 to the right. So for instance, you have the number 111, which is 3, but then you make it 110. So that then becomes 6, which is double that value. And that phenomenon happens over and over. So now it's 12. Now it is 24. So as you add zeros to the right, your values actually double in binary because it's base 2, right? So instead of being multiplied by 10 in base 10, as you add zeros to the right to a binary number, the value gets multiplied by 2. The next question is, do binary numbers 001 and 000011 have the same value or different values? So again, we can take a look at this. So what they're asking is this value the same as this value? And is that the same as this value or this value? And it turns out that yes. As we add more zeros to the left, it doesn't have an impact on the value because we're not adding any of these place values, and we're not modifying which position that we're actually adding to our overall value. This is always going to be 1. So there's no effect since the zeros to the left don't affect the total value. And then the last question is, would 2 bits be enough to assign a unique binary number to each vowel in the English language? In other words, can you represent, I could not count up to, but can you represent 5, at least 5 values, because there's 5 vowels in the English language, using 2 bits of binary. So in 2 bits of binary, we can have, so just using these, we can have 0, right? We can have 1, and we could also have 2, which is 1 0, and then we can also have 3. So that's 4 different values. So no, you can only represent up to, 4 different values. You can count up to 3, but it's 4 different values, counting 0. So you would need at least another bit here in order to represent 5 values, because with 3 bits you can count up to 7, 4, 5, 6, 7, which means that counting 0 you can represent 8 different values, or such as a vowel or anything like that. All right, so that's the end of the recap for this homework assignment.